So now we're going to look at one way of applying the ideal gas equation, and we can use this to determine the molecular mass of a gas. Of course, the molecular mass is the same thing as the molar mass, numerically speaking. So in fact, what we'll be doing, what I'll be showing you here is how to determine the molar mass. And basically, once you determine the molar mass, then numerically, it would be the same as the molecular mass. So what we're going to do is let uppercase M represent the molar mass and lowercase m represents the mass in grams. So if that's the case, that means that the relationship between these three terms is given right here. The molar mass is the mass in grams represented by lowercase m divided by the number of moles, which is represented here by n. So we can rearrange this actually to get n is equal to lowercase m divided by uppercase m. Now, as far as the ideal gas equation is concerned, we can rearrange that also to get an expression for n. N, in this case, would be equal to PV over RT. So we have n equal to these two expressions here, so we can equate these expressions to each other like that. And then we can rearrange it to get a solution or an expression for uppercase M, which is a molar mass. So it turns out that when you solve for uppercase M, the molar mass, that will be equal to the mass in grams times R, which is a molar gas constant, times the temperature in Kelvin, divided by the pressure, which would be in atmospheres, divided by or multiplied by the volume in liters, right? So that's basically how we can determine the molar mass of a gas if we have all these terms. If we have the mass, we have the temperature, the pressure, and the volume, then all we have to do is plug the numbers in, and we end up with the molar mass value, which, as I said before, is the same thing as the molecular mass. Okay, so what's in this box here is stating that an alternative way of doing this, which is basically the same thing, but another different way of doing this, is to find n and then divide the mass in grams. Well, firstly, find n using the ideal gas equation, like this, and then once you find that n, then you divide the mass in grams by that n value, which is a moles, and that will give you the molar mass. So basically, just another way of doing the same thing. Personally speaking, I prefer to just use this equation directly, all right? Okay, so here's an example of a question involving the use of this equation. Now, in this question, they gave you the mass of the gas, they gave you the volume, they gave you the pressure, and they gave you the temperature in Kelvin. And the question is asking for the molecular mass of the gas. So the equation, of course, is uppercase M is equal to mRT over PV, all right? So all we have to do is plug the numbers in. So M, the mass in grams, lowercase m, that's 0.550 grams, times R, which is a constant, 0.0821 liters atmospheres over mole Kelvin, times the temperature in Kelvin, which is given as 289 Kelvin. And then we divide all of that by the pressure, which is 0.968 atmospheres, multiplied by the volume, which is 0.200 liters. Right? And again, I think I mentioned this before, and I'll mention it here again, just in case I didn't before. Whenever you're using equations like these and plugging in the numbers, make sure that you include the units as a part of the process, because as you're going to see that in this case, certain units will cancel out and you'll be left with other units for the final answer. So in this particular case, the atmospheres will cancel out here and here, the Kelvin will cancel out here and here, the liters will cancel out here and here, and whatever answer you're going to get will be expressed in grams per mole, all right? So the final answer will be expressed in grams per mole, which of course would be the units of molar mass. And all we have to do from here is number crunching. So 0.550 times 0.0821 times 289 divided by 0.968 times 0.200. And according to my calculations, this works out to be equal to 67.4 grams per mole. So that's basically how that is done, right? Basically, you just plug the numbers that are given in the question into the equation and you solve for the final answer. Okay, so that's how we apply the molar mass equation. Oh, by the way, we're not finished yet because the question is asking for the molecular mass. So therefore, we need to add a statement saying that the molecular mass is equal to 67.4 AMU. All right, so remember the difference between molar mass and the molecular mass would be the units. AMU for molecular mass, grams per mole for molar mass. And the question is asking specifically for the molecular mass. All right, okay, thought that was important to point out. Okay, here's another example. Now, this one is a bit more complicated because you have to do some conversion of units. So while you have to plug the values directly into the same equation, you have to convert the units so that everything can work out in terms of finding the final answer. So we're using the same equation here. M is equal to MRT over PV. And in this case, again, the question is asking for the molecular mass. The question gave us the temperature in Celsius, the pressure in torr, the volume in milliliters, and the mass in grams, all right? So basically, we need to plug the numbers in, starting with the mass, which is 0.523 grams, times R, which is always going to be 0.0821 liters, atmospheres, over mole Kelvin, times the temperature. What's the temperature? 100 degrees, but we have to convert that to Kelvin. So that means we have to add 273 to this, and that will give us 373 Kelvin. And then we divide that by the pressure. What's the pressure? Well, they gave the pressure as 755 torr, but we have to convert that to atmospheres. So that means we have to multiply this by the appropriate conversion factor, where we have 1 atmosphere above as a numerator and 760 atmospheres torr below as a numerator, right? So that's how we convert from torr to atmospheres. Then we multiply that by the volume, and they gave us 185 mils as a volume, but we have to convert that to liters. So again, we have to multiply by the appropriate conversion factor, which in this case will have 1 liter above and 1,000 mils below. All right, and we work this out. Now again, as you can see, I've placed units appropriately where they belong, and you're going to see how they cancel out. For example, the torr units will cancel out here and here, atmospheres will cancel out here and here, Kelvin will cancel out here and here, liters will cancel out here and here, milliliters will cancel out here and here, and I think that's it. The only units remaining would be, again, grams per mole. So that would be the units resulting from this calculation here. So now we have to do the number crunching. 0.523 times 0.0821 times 373. And then we divide that by 750, which would be divided by 760. And then divide by 0.185. So according to my calculations, this works out to be equal to, let me do this down here. So that's the answer, 87.7 grams per mole, which means, again, like we did the last time, excuse me, we have to state that the molecular mass is equal to 87.7 AMU. All right, and that's basically how we do that. All right, okay, so I'm going to stop this video here, and I'm going to talk about gas densities in the next video. All right, okay, until next time.